So there's Anycast in this presentation, but not the scary kind. This is a tame, sort of self-contained, caged Anycast, not the wild, rampaging Anycast we heard about before. So what I'm talking about here is building clusters of services or clusters of hosts to provide a service, and in particular I'm talking about the DNS. I'll mention very briefly at the end how this might be applicable to other protocols and things, but I'm really just talking about DNS here. So our starting point with this, without deploying any of the stuff that I'm about to describe, what do people have? Well, for authority servers, people have several servers authoritative for one zone or multiple zones, at least two, hopefully more. They're hopefully dispersed geographically. They're not in adjacent addresses on the same switch. So that's authority servers. And for recursive resolvers, they have several, hopefully two. And these are the things that clients use to look up names. So before we start considering enhancements we can make, it's sometimes useful to work out what's broken in the first place. So we have single points of failure in delivering this DNS service in both cases. We have an issue with maintenance windows. If we want to take one of these hosts down for maintenance, the service gets degraded to some extent. And if we need to scale the service to support higher request loads, then we have individual servers that we need to upgrade, which again impinges on the maintenance windows. And if we scale vertically per server, then maybe we have some sort of limiting factor or limit to the number of queries we can sustain on a single platform. So these are the things that are kind of broken. So for authority servers, it's not actually that broken. If a zone has multiple NS records, multiple authoritative servers, then resolvers are generally pretty good at trying different servers, and then they cache the results anyway. So if a single server in an NS set is down, chances are that the people trying to actually use the DNS servers to look up names probably won't even notice that the servers are down. It does depend a bit on how important the zone is. Obviously, if you're serving the root zone, then you hope to have high availability for all the servers. If you're serving a zone that is a lower profile sort of zone in the world, then probably having a server or two out of commission at any one time for maintenance or unplanned outage is tolerable. For recursive resolvers, it's actually more broken. And this is because clients are generally quite stupid in using more than one server, even if you provide them with more than one address to use for a recursive resolver. They'll use one, they'll take a long time to time out, and then they'll use another one, and quite often they won't learn. The next time they do another lookup, they'll go back to the same broken server and do another timeout. And for users, that means that the internet is broken. And when the internet's broken, the help desk phone rings, and everybody gets very stressed. So in terms of the help desk phone metric of brokenness of the internet, then recursive resolvers are quite important. So some solutions for doing this kind of stuff, in fact, building clusters in general, there are commercial products you can buy from people like Sun and HP that will do this. You can stick commercial load balancing appliances in front of multiple hosts made by people like Cisco or Nortel Foundry. You can kind of use CARP, which is the OpenBSD-derived VRRP thing. And I actually understood briefly once how people said you could load balance using CARP, and then I decided that it wasn't really applicable to this. But I've long since lost my reasoning. So that's not very convincing. But I think CARP is not particularly applicable in this, but maybe it could be shoehorned into something approaching it. And the last approach I've listed here is the one we're going to talk about here, which is Anycast with deliberately equal cost paths and flow hashing. So all of the things on the previous slide have the common requirement that the service that you're trying to distribute across a cluster has an IP address associated with it that's independent of the infrastructure that provides the service. So the Arrowpoint, Alteon type people used to call this a VIP, which was confusing at the time that we had VIPs in routers. Virtual IP, a gratuitous use of the word virtual. And this can be useful for other reasons than just load balancing. This can be useful, for example, for having a stable address for a service that allows you to move the service between machines if one machine is taken down, or maybe to move a machine between sites. So our Toolbag here in our open source solution is to use some kind of Unix type operating system. We use FreeBSD at ISC. To use some kind of DNS software, obviously we use Bind. And to use some kind of host-based routing protocol implementation, we've used Zebra and Quagga. We've also used GateD in the past. Something that can talk OSPF in any case. And this is generally what it looks like. So what we have for IP addressing, we have a globally unique unicast address on every single host, and we have the same service address configured on loopback addresses on multiple hosts. The routers and hosts communicate within some sort of layer 2 fabric, a VLAN through a switch, maybe just one switch, maybe multiple switches. The hosts are autonomous. So what I mean by that is any host on its own is capable of providing the service functionally. It may not be able to handle the load of service. It might require more than one host to scale. Hosts respond to requests on the service address and are managed by their unique unicast addresses. So what this means is that a request will come in with the destination address, which is bound to a loopback address on the host. The response will go back with the source address set to that same service address. But if you're trying to manage the host, you don't use those Anycast addresses. You use the unicast addresses, which are unique. The routers and hosts speak OSPF, and the reason they do that is so that the hosts can originate routing information for that loopback connected service address towards the routers, which provides the routers with a way to route requests to those addresses to the hosts, and the routers in return originate a default route back to the hosts. So requests from the internet are routed down through the top of that cloud, through one of those routers, towards one of those hosts, and the response generated by the host is sent out towards one of the routers, and life is good. And I've ignored all the difficult parts, which I'm now going to describe. So first of all, on the routers need to be able to support equal cost multipath, which means they have multiple candidate routes to the same destination. So this is for the application where we're trying to share load across a collection of hosts. We're not just trying to provide some sort of failover in the event of failure. So the routers are actually capable of installing multiple routes in the FIB and varying the route that they use for inbound packets using some heuristic. And most commercial routers have no problem with this. However, host-based routers generally do, and that's usually a restriction of the kernel. The idea of having two identical routes to different destinations is not something that works well with free Unix routing code. Most DNS queries are carried over UDP, and for UDP datagrams with no fragmentation, transaction is just a single request packet, single response packet, and basically everything we've described up till here is sufficient to handle that case. Transactions that are carried over TCP obviously involve more than one packet. So the important thing here is that we need all the packets associated with a single transaction to be delivered to the same host. If we get different packets in the TCP setup sequence which are delivered to different hosts, then it's not going to actually result in anything good. So the way we do this is we tell the routers to use a hash-based algorithm to select one of the candidate routes for the destination according to something which identifies the flow. So we take a hash of something like a source address, destination address, source port, destination port, protocol, something like that which is sufficient to identify a single flow. And we use that to identify which of many candidate routes the routers should use when they deliver a packet towards the host. The idea here is to keep all the packets associated with a single flow delivered to the same host. So here we have the same thing in pictures. On the left, we have the possible set of results for a hash function on some collection of stuff which defines a flow. And we just say we have three candidate routes for this destination. We'll take the first third of the hash space and route that towards the first route. We'll follow the second route for the next third, and we'll follow the last route for the remaining third. So on Cisco's, we do this with Ceph. Turning on Ceph just makes this happen. And on Juniper's, we use load balance per packet, which does a similar sort of thing. There's actually a bit more Juniper configuration required, but. So the hash table is per router. If we have more than one router, we have to make sure that the packets associated with a single flow are also delivered to the same router. Because if we have multiple packets or different packets in the same flow delivered to different routers, then that hash algorithm is going to produce a different result. So we might end up spraying the requests over multiple hosts, even though an individual router wouldn't do that. So we can do a few things. We can avoid ECMP routes altogether. We can turn on Ceph everywhere. So we have some deterministic hash-based destination through the network for any given destination. Or we just use routing protocols that don't support ECMP. Or in fact, we have a topology that has no multiple paths at all, or has a choke point somewhere where you only have a single path. But again, that's probably not realistic. The idea is to make things more reliable. So this is pretty easy, but at least I have the only slide so far that has router configuration stuff on it. This is a... Oh, VJ did. That's true. That's true. I take it all back. So we turn on Ceph. That's basically it. That's the thing here. We have an OSPF process running. No rocket science here. The hosts have no need for ECMP support because the hosts just need to send a packet back to the world. And the address that they're directing their packets to is not Anycast. It's the source address of the original query, which is unique in the world if the client expects to get a response. The availability of the service is signaled to the routers using LSAs. So if one host decides it's not going to participate in providing a particular service anymore, it just basically withdraws the route corresponding to that service. And then it no longer receives traffic with that destination address. So here's some Zebra configuration, which looks remarkably similar to the Cisco one. There's no real complicated bind configuration required to make this work. The key parts are that you bind to the service address for receiving requests, and you use the unique unicast address for everything else. So if you're doing zone transfers, you don't source those from your Anycast address. You source them from the globally unique unicast address. So there is a slight complication here because we have a large number of people in the world who still think it's a good idea to restrict zone transfers based on source IP address. And somebody else in the world who's asked you to be a slave for their zone doesn't necessarily know or care whether you have a single name server or whether you have a cluster of name servers. They just want the request to come from the one address which corresponds to your name server, which is the service address. So in this case, we have a problem. If these are slave servers down at the bottom, these hosts, host 1, host 2, host 3, and host 4, then when they source their zone transfer attempts from the Anycast address, which is bound to the loopback address, then only 1 in n requests is going to succeed, because you're basically waiting for the one lucky host which corresponds to the hash for the return packets pointing at the same host. So this is a bit messy. What this means is you have n hosts, and most of them are going to fail most of the time. Every now and then one of them will succeed. So you can mitigate this. It's still ugly. But what you can do is configure each of these hosts to do zone transfers from each other as well as from the master server. So you rely on the fact that most of them are going to fail when they try and contact the master server. At least one of them will succeed occasionally. And when that one does succeed, it will basically spray the information towards the other hosts. The sane alternative to this is just use tsig instead and stop using source addresses as an ACL. One thing that we need to make sure of when we build clusters like this is that if a name server goes bad, we don't want to send requests to it. Now what we do with our clusters that we build with bind 9, we rely on the fact that bind 9 is riddled with assertions. And if anything happens within the code which suggests that the name server has turned itself into an unexpected state, it will dump core. So this is named dumping core as a feature, officially not a bug. So this is actually quite nice from the point of view of configuring these clusters, because we can write a pretty simple wrapper around named. We can run it, we can stop it demonizing, we can wait for it to dump core. I should put an if in there somewhere, but we'll wait for when it does dump core. And when it does, we can pull down the loopback interface corresponding to the service, which will trigger an LSA, which will basically remove that node from service. We then might do something like wait 10 minutes, then start it up again to avoid flapping. But basically what this means is we can tie the availability of the service with the routing information to whether or not the server itself is running. Common to pretty much all these approaches that I listed here on the third or fourth slide in for building these clusters, and also for most other applications of Anycast, is the problem of service monitoring. Building enough infrastructure to be able to reliably monitor these things is difficult, and it's arguable as to whether you can reliably monitor them absolutely at all. You can check individual hosts to make sure that the individual hosts are working, but you're not necessarily checking the Anycast addresses unless you check from the host itself. So you're not really doing a test that's representative of what happens with real clients in the real network. In bind 8 and in bind 9 from 9.3, we have this thing called hostname.bind in the class chaos, which if you query it and look for text resource records, you'll get a string which returns the name of the server. So in terms of trying to troubleshoot a name server which appears to have gone bad, this can be of some use. Not especially a huge amount of use, because of course you're sending a different query to the one that was causing the problem. There is apparently, well, there's continued talk of an EDNS extension which will actually allow this kind of instrumentation to happen on a real query. So you can get an answer back which also contains some indication of the host name or the instance of the node that answered it. But nothing like that is deployed right now. The main issue here for troubleshooting is that you have the potential for customers to call up and say this name server is not working, and you have the help desk checking it and saying, well, actually it is because I just checked it and it's fine. And everyone is gleefully ignorant of the fact that there are multiple servers deployed and they might both be checking different servers. So as I say at the bottom, the customer is not necessarily lying. I'm not sure that's a good general rule, but it's... So limitations of this particular technique, the commercial load balancing appliances that I mentioned some of earlier, they usually have a large number of different heuristics or different approaches they can use to choose candidate routes or to choose individual hosts in a cluster, like least recently used, least loaded server, things like that. This doesn't. This is far more clumsy than that. As I mentioned, doing rigorous real-life tests is next to impossible with this stuff. You can get a fair degree of confidence that all the nodes, all the hosts in the node are working, and you also always have the help desk phone ringing metric to confirm that nothing is in fact wrong. But in general, it's not possible to determine exactly which host answered any particular query. So this is a problem. Now, in terms of actually deploying these things in a network, what this boils down to is having people who normally look after servers participate in IGPs with routers, which in small organizations like ISC, when the host people and the router people are sometimes the same people, that's not really that big a deal. But in bigger networks, the idea of systems people coming and saying, well, we have this Microsoft server and we'd like to do Anycast, so we want this Microsoft box to talk OSPF to your network. It's not necessarily the most popular idea that could be floated. So you can get around this somewhat by making small server-specific IGPs. So you effectively build a firewall. You have a completely separate area which just has the servers talking to some routers. And you carefully redistribute the routes backwards and forwards. So at least the flapping is isolated to a particular area which doesn't affect the rest of the network. So as I mentioned, I talked about DNS in this presentation, which has the sort of peculiar characteristics that most traffic is stateless. And the traffic that isn't stateless, that is stateful, is comprised of transactions which are generally pretty short. This is obviously not the same as most protocols which happen on the internet. In general, deploying Anycast with stateful protocols is a minefield, and you have to be very careful. But that's not to say that it can't be done. There are a large number of variables with node placement and the nature of protocols, the nature of the routing systems and who runs them, which all mixed together in a giant cauldron could produce the answer that Anycast is a very sensible thing to do. But in many cases it doesn't. However, I don't think it's reasonable to say that Anycast and TCP never mix and can never be made to work, because it's clearly not true. It clearly does work a lot of the time. You just have to be careful and consider that you need the right tool to fix the right problem. So related to this, and most often found in the case of a recursive server, is the idea of just distributing a service throughout an IGP. Not just building a cluster in a single rack attached to a single switch or a pair of switches, but taking some service like a recursive resolver and sticking, for example, one box in every POP, all numbered with the same address, so that any time a user tries to use a local name server, they do really use a local one. I've seen this deployed in many places. It was perhaps more common to deploy things this way back when links between POPs were very expensive and very slow. So that if you could answer a query locally without touching the 56K link, then that was a big win. But there are certainly people who still do this. And it has similar sort of issues surrounding it as the cluster project that I just described. The only possible difference really is that the load sharing considerations are different. There may be no ECMP routes between the different name servers. The other related exercise is the global distribution of a service using Anycast, which is what the previous two presentations were talking about measuring. And the key difference between this and the thing that I described is that the global Anycast idea depends on other people's networks. It arguably it involves less ECMP issues, although some of the measurements suggest that that's not zero, and the routing protocols use a difference. So there are some key differences there that make this kind of different. And that's all. Are there any questions?
David Nolan, Carnegie Mellon University. We've been doing DNS via Anycast in our local area with OSPF for some time, as you're probably aware, because I think you know Kevin Miller, who used to work for us and did the original deployment. On the service monitoring issue, we definitely saw similar things to what you're talking about. If the Quagga daemon on one machine failed, we needed to know that, things like that. The approach we've taken to that is actually assigning an additional Anycast address that's unique to each server. So in addition to the one that the service is running on, there's one per machine, and we monitor on those so we know if we can talk DNS on that IP, then that particular machine is running DNS and running Quagga.
How is that not a unicast address?
It is a unicast address, but we're announcing it via OSPF and only via OSPF.
Oh, that makes sense. Right.
There
are still some failure modes that wouldn't pick up, but it would certainly
it's only announced as a /32, right. And it's in the same range of addresses as all of our other addresses.
So it helps you in the case where Zebra goes mad and tries to take over the world.
It's also helped us in the case of noticing a router losing OSPF adjacency with that server because the router load spiked, and we've seen that actually very recently. The other thing that we've had recently is we re-engineered our entire network and deployed HSRP everywhere and discovered many interaction problems with HSRP and OSPF Anycast because now all of a sudden we had routers who could see each other across more than one link. Because in addition to seeing the Anycasted server speaking OSPF, they saw the other member of the HSRP pod over that same network. And that led to interesting problems, and we had to come up with some interesting rules on how to solve it. So
that's interesting.
It might be a topic for a paper I do at some point.
Thanks. Anybody else? Nope. Thanks very much.